Okay, ma'am.
This was there in C5, right?
Yes, ma'am.
No, we have started D1.
No,
It's a
yeah.
D1
C5, we
topic.
completed C5, we are in D1.
Yeah, we are in D1, na? Then I am correct.
Yes,
Good. And so Kepler's third law we have started.
yes, ma'am.
Just check. Black holes, the solar system. Okay, done. Now I got it. So we have to start the Kepler's laws of orbital motion, right?
Yes, ma'am.
That is what we have to start. Yeah. So first, let me give you the laws, and after that, we will discuss that.
Okay, ma'am.
Okay. So I'm discussing with you the Kepler's laws. Already third law
Yes,
has been
ma'am.
discussed. So I'm discussing right now the first and the second law.
We were discussing the like we were deriving the formulas.
Yeah, here it is. Third law, isn't it? But I'll discuss it again. Don't worry.
Yes.
Relax. Okay. So Kepler's laws of
Yes.
orbital motion. First law says us that the planetary orbits are elliptical in shape and star is the focus point of that. Okay. It's a very easy law that he suggested. Kepler has suggested that the orbits are not circular, but they are elliptical. Done.
Yes, ma'am.
They are elliptical in shape and they are not circular. Done. Second law suggests us that
Yes,
the radius vector from the star to the orbiting body sweeps equal area and equal interval of time. See, this is the area and this is the area. So obviously when it is going further away from the sun, then it will be having less speed because the distance is high and speed is directly proportional to distance. So it will take longer time here. Whereas if I compare it over here,
yes, ma'am.
the speed will be very high as the distance covered is very, very high. Hence, the time taken would be smaller. Correct?
Yes, ma'am. Yes, ma'am.
I think. Are you getting or not? It's a very simple law. Speed equals to distance over time.
Yes, ma'am.
Okay, Akshita. It's not a tough thing that I'm saying. Yeah. Hello. You are audible.
Okay, ma'am.
Yeah. Yeah. Relax. Relax.
Yes.
Say. Are you saying something?
No, ma'am. Your voice was just like little bit like slow, so I was just like not sure if you
Acha,
could.
acha. I was thinking. I was not saying anything. Okay.
Okay, ma'am.
Yeah. So I'm saying that speed equals to distance over time. So how much is the speed? That much will be the distance covered. So here the distance and the speed is less. That means what? Time taken would be very high. Correct?
Yes, ma'am.
Because speed is inversely proportional to time, no?
Yes, ma'am. I understood,
Okay.
ma'am.
Yeah. So that's why the second law is like that. And first law is also very simple that if I form a ellipse, then just have a look over here. This a circle. This is a circle. Here is the center. Here is the center. Joining the two lines, if I make it a ellipse, it will be like this. So I'll be having two focus. Focus 1 and focus 2. So at one focus, we place the position of sun and the planet revolve around it. Okay. So this is the first law. Understood?
Yes, ma'am.
Okay, now let's come to the third law. And
Yes.
that is the square of the orbital period is proportional to the cube of the semi-major axis of the ellipse. Okay, That is obviously
Yes.
your T square is equal to R cube. See here. T square is equal to R cube. Okay?
Yes, ma'am. Yes, ma'am.
Okay. So that means the square of the orbital period, that means the one oscillation time period, okay, is proportional to what? Cube of the radius of the semi-major axis. Where is the semi-major ellipse we are having? Here. Check.
Yes.
Okay. Fine.
Yes.
Let me draw the conclusion for you, and after that kindly solve one question for me.
Okay, ma'am.
But you have to be quick.
Yes.
Okay. So here is the third law, and that states that the square of the orbital period, this is the third law.
Okay.
Okay. The square of the orbital period is proportional to the cube of the semi-major axis of the ellipse. That is the distance from the center of the ellipse to the farthest point on the perimeter. Okay. That means this distance.
Yes, ma'am.
The R cube of this is proportional to the T square. The time it is taking, the square of that is proportional to the R cube. Understood?
Yes, ma'am.
Yeah. R cube is what? Farthest point radius. Okay.
Yes, ma'am. Yes.
Okay. So now let's calculate the energy of an orbiting body.
Okay.
What will be the energy? It will be very, very simple. That the potential energy will be given as minus GMM over R square. Correct? Over R. Done. And the kinetic energy is given as half mv square. Correct? I had
Yes,
explained you yesterday how to find out potential energy. Potential energy is nothing but work done.
MGH, which is
And work done is nothing but F delta S. F is nothing but GMM
Yes, ma'am.
over R square. This is also our RR got cancelled, so I got this formula.
EMM.
Okay?
Yes, ma'am.
Yeah. So obviously, approximation is that in the circular orbit, what do we say that our centripetal force that is provided by the star to the planets is given with the gravity. Correct? That means what? My GMM over R square is given by MV square over R. Correct or not?
Yes, ma'am.
Okay. Now, let's rearrange and multiply this by half. Okay. So, when I rearrange it, I guess 1R and 1R will get cancelled from here. Right?
Yes, ma'am.
Similarly, small m and small m will get cancelled out.
Yes, ma'am.
But do we need to cancel m? We require m over here. Okay, don't cancel m because we are in requirement of that. Okay, yeah, but r and r will get cancelled out. Okay, so it will be half of mv square is equal to, this is square. Okay,
Yes, ma'am.
equal to what?
GMM by R.
G capital M small m over 2r. Correct?
Yes, ma'am.
Check.
Yes, ma'am.
Okay, done. So the kinetic energy is GMM over 2R. Correct? Because half mv
Yes,
square is
ma'am.
what? Kinetic energy. Isn't it? So my total energy will be potential energy plus kinetic energy, and that will be nothing but minus GMM over R plus GMM over 2R. Okay.
Yes, ma'am.
So the total energy will be minus GMM over 2R. Correct?
Yes, ma'am.
Done. So this is the total energy that I have got. Now after this we are having new topic, and that is Earth satellite.
Yes, ma'am.
Okay. So basically the equations here we are having, that is for orbits, planets are also applied to the satellites also. Done? Around the Earth.
Yes.
Done? So this means
Yes.
that the satellites are closer to the Earth and they have a time period much shorter than in comparison to the satellites which are farther away. Correct?
Yes, ma'am.
Because they are having higher speed.
Yes, ma'am.
So time will be short, right? So
Yes, ma'am.
similarly, for example, if I have a low orbit spy satellite that could orbit the Earth, it will be taking once every 2 hours. It will take a round around the Earth. Okay. And it is much higher for a TV satellite orbit that only orbits once in a day.
Yes, ma'am.
Okay. So we have geostationary satellites and we have polar satellites. Like that, we differentiate. Okay.
Yes.
Because polar satellites are farther away in comparison to your geostationary satellites. I mean, not geostationary, but your one is polar and one is equator satellites, equatorial satellites. Done?
Yes, ma'am.
One is passing, if suppose this is my Earth, one will pass through the north-south pole, one will pass through the equator. So it is like that.
Yes, ma'am.
Okay. And let me give you the correct idea of that. So basically polar satellites, that means this north and south pole satellites, they revolve around 200 to 1000 kilometer above the Earth's surface at an altitude of 200 to 1000. Done. Then we are having next satellite, and that is equatorial satellite. And they are at nearly, not this one, sorry, my bad. They are nearly at 35,786 kilometer above the Earth's surface. Understood?
Yes, ma'am.
Okay. Any doubts still here?
No, ma'am.
Okay. Now suppose you imagine that you are in a spaceship, okay, and you are orbiting the Earth at a very low altitude. Then to move to a higher altitude, what you have to require? You have to use basically the rocket motors to increase your energy, right?
Yes, ma'am.
And if you keep doing this, you will move away from the orbit to the orbit, and like that, and you will get more further away from the Earth. Correct or not?
Yes,
So
ma'am.
that means the energy of the spaceship in each of the orbit can be different. Am I making sense?
Yes, ma'am.
Okay, let us calculate that how much energy does it require. So for each altitude, it have this much of energy. Check. Okay. Here is the total energy, the green line, and this is the orbital radius. So as the radius is going away, how much energy you require, that is shown here. So very first you require a very high kinetic energy, and a very high potential energy is getting converted into kinetic energy, right?
Yes, ma'am.
Now as the orbit is passing from one to another, one to another, one to another, the radius is increasing, you will require more and more and more energy. Done? So the total energy is minus 2 GMM over 2R. Okay. And here from the graph, even we can predict that low satellites have greater kinetic energy, but less total kinetic energy. Can you see that?
Yes, ma'am.
higher kinetic energy but less low total energy. Done?
Yes. Yes, ma'am.
In comparison to
Yes.
the distant satellite. Am I making sense?
Yes, ma'am.
So although the distant satellite move with a very slower speed, okay, and basically what happens is we have to do the work to increase their orbital radius. Okay,
Okay, ma'am.
because they have a very low kinetic energy, but the orbital radius have got increased. So that means what? The total energy will be increasing. Understood?
Yes, ma'am.
So the satellites in the low Earth orbit are not completely out of the atmosphere. So they lose the energy due to air resistance and hence they lose the energy and they move towards the spiral. That is like in towards the Earth, they will move in a orbit. Okay.
Yes, ma'am.
It will not be asked in so much depth from you. Okay, in the exam, but yeah, they can ask you that why the farther of satellites require more energy. So obviously in the start, the kinetic energy high, but the total energy is low. Check, it is in minus. But as you go away, you will require less kinetic energy. Now the kinetic energy had come to zero, but the total energy have increased from minus to this much. Understood?
Yes, ma'am.
So this much only will work for you. Don't worry about that. Okay, let me give you some questions. But I'm giving you just 2 minutes and 5 minutes to solve these questions. Okay, not more than this.
Yes, ma'am.
So for the first question,
Is there any given for the first question, ma'am?
yeah, I'm giving you for question 17. No, I know you are asking this much. Okay, but you
Yes.
need to be quick, Akshita.
Ma'am, is it like the number
Okay, you
mm,
need the radius
I
of the
can't
Earth
see any number.
6,400 kilometers. The radius
Okay,
of the
ma'am.
Earth is 6,400 kilometers. Yeah, it's written here. Check.
Oh,
Some informations are fixed. You need to apply
oh,
at your own. Shall I give you those
yes.
numbers?
No, no, ma'am, it's fine.
Like the mass of Earth is fixed. Okay.
Yes, ma'am.
Radius of Earth is fixed. Yeah.
Ma'am? Ma'am?
Yes, say.
Uh, First I read the last
The
question.
answers?
So for the first one, it is 1 second, ma'am. Where is 1.5? Minus.
Kindly be quick,
Uh,
Akshita.
yes, ma'am.
Yeah.
Last. I will come from the last question, ma'am, because that's in my calculator. Last question and last question C part is minus 5.31 to the power 10. And then for the
Give me a second. I'm just opening the answers. That is D1 chapter, no?
B one is
Yeah, it is D1. Okay. So 17th answer. What did you got?
17th one I did do, ma'am. Is it like time period is equal to 1 day means should we
So that
take
they
it
move
with
about the same point on the TV satellite have the time period equal to 1 day and calculate the radius of their orbit. So we have to calculate the radius of their orbit. That is what they are saying. Okay. So what formula we can apply? Tell me.
we can apply the GM M by R square if we
Okay.
have RNA.
Go ahead.
But for to find uh, time,
Mm-hmm.
calculate the radius of orbit. Mm, some formula with the unit in if GMM by R square by M minus GM by R root 2 GM by R. But there is no formula with uh, specifically with time minute.
Mm-hmm. Time period formula is there, no? 2 pi under root L over G. Sorry, L over R. So here we can apply the same formula. 2 pi under root R cube over G M. If you remember, we have done it in the last class.
Yes, ma'am, but
Check.
it's not in the data book.
Capital T equals to, here it is. T equals to 2 pi under root R cube over capital G capital M.
Yes, ma'am.
Okay.
I was looking at the data booklet. I don't think this was.
No, sometimes you need to be sharp. This formula just before a few seconds I had taught you.
Yes, ma'am. But
Okay.
since in exam I use the data booklet, so I follow that method to solve the question.
Yeah, that is perfectly fine. But everywhere, I don't think formula booklet will work for you.
Yes, ma'am. I have to memorize this.
Okay, connecting formula should be there in your mind. See, I'm giving you the question as the data has been provided. Okay, so we cannot waste much time over this. But when you are solving it with this formula, you will get the answers. Okay, so let's go to the next. Second also will be sorted like that. Let's go to third. These formulas already are here.
Yes, ma'am. Third
Okay.
question I have done that.
Yeah. Okay, give me the answer.
A is 1 second. My 1 point. 5.86 into 10 to the power 10. And B is
So it will be 5.9 basically.
yes, ma'am. 6 point.
And it's not 10 to the power of 6, 10 to the power of 10.
10 to the power 10, ma'am. 10 to the power 10. And then minus 1.17 into 10 to the power 11 for B. And then for C it is minus 5.31 into 10 to the power 10.
Okay. So in B it is 1.2 into 10 raised to 11. Whereas you had given me one. Yeah.
Minus 1.172 into the power 11.
Yeah, so that will be 1.2 only, and 10 raised to
11.
okay. How about C 10 raised to?
C is 10 raised to 10.
Okay, and 6.1 it is
6 point, that is 10. 10 is 2. So 6 point, 5.86 in 10 to the power 10.
okay. Okay, let's start with the D2 topic, and the D2 topic is electric and magnetic fields. Okay, so I'm starting with this. Very first topic is electric force. So what do we understand by electric force is basically, suppose here I am having a charge plus Q, how much electrostatic force it is experiencing due to the electric field area. Okay, so the electric force is defined as, or electric field is defined as, force experienced by per unit. Here we will not use mass but per unit charge. So the formula for the force will be E into Q. Understood?
Yes, ma'am.
Okay. Now forces could be of two types in electrostatic, and they are basically repulsive in nature and they are attractive in nature. Okay.
Yes, ma'am.
Okay. Then after this, if we are doing study of attractive and repulsive, you need to understand how it is given. So it is given by Coulomb's law. What does the Coulomb's law suggest? Again, it is as simple as your gravitational law of universal law of gravitation, and that is when you place two charges, let's say plus Q, let's say here minus Q. So it will going to attract each other, and you have to remember this, that from plus Q charge, you will have your radial field of lines in the outward direction, whereas for minus Q charge, you will have your radial direction in the inward. Why? Because the electric field always travels from plus to minus. Okay,
Yes, ma'am.
you need to write it because it's very important.
Okay.
Just give me a second.
Yes.
Okay, I'm back. I'm really sorry. Okay, so after this, let's do the study of that. So it is given by basically the Coulomb's law, as I said. And what does the Coulomb's law suggest us? Coulomb's law suggests us that if you place two charges, are you there, Akshita?
Yes, ma'am.
Okay, if you place two charges to each other which are at a distance of, let's say, r from each other, and they are obviously from their centers, because if you have a sphere like this and here it is a positive charge, then it will be spreaded at the surface. So the charge force will be highest at the at the surface. Okay, inside it
Yes,
will
ma'am.
be completely zero and outside it will be gradually decreasing. Okay, as you go away. So this is the potential field as I have discussed. So here, let's come back to the pointer. So this actually suggests us that the electrostatic force is directly proportional to the product of the two charges. Product of the two charges means magnitude of the two charges, and also it is inversely proportional to the square of the distance between them. When I actually combine it, I will be getting q1 over q1 product of q2 over r square. Done. And this is directly proportional. Let's convert it into equality symbol. So the proportionality constant, that is the electrostatic force, is equal to 1 upon 4 pi epsilon naught q1 q2 over r square. So this is the electrostatic force which is given by the Coulomb's law. Okay, where 1 upon 4 pi epsilon naught is the permittivity of the field, or permittivity of the medium. Done. Now what is the permittivity of the medium? That if suppose here are the field lines and here I am placing a charge. Okay, so how much tendency do these field line have to actually pass through this field successfully? Okay, that will be the permittivity of this particular region around the charge. Okay,
Yes, ma'am.
any doubts?
No, no.
Okay, very good. So this is it. Now, after this, we are having, let's do a study about the charge. So what is a charge? The charge is basically defined as the property of the matter that causes the electric force. Okay.
Yes, ma'am.
Okay. So the property of the matter that causes the electric force is known as charge. Okay. Now here, there are two types of charges, obviously plus and minus. If you have excessive of the electrons, okay, then you get negatively charged. When you get lack of electrons, then you will get positively charged body. Okay, so these are the two charges that we are having. Now, these charges are obviously scalar in nature and their SI unit is Coulomb. Okay,
Yes, ma'am.
now after this, let's do the study of their properties. So the very first property of charge is they are integral multiple of their charge. Okay, like something is having plus 1 charge, so it will be integral multiple like plus 2, plus 3, plus 4, or minus 1, minus 2, minus 3, minus 4. It will never ever be this. These all are correct, but it will never be minus half, minus 1 by 3, plus 2 by 3. It will never be like this. Okay, so it is integral multiple. What is the second property? So the second property says us that they are attractive as well as repulsive. Okay, they can attract and they can repel also. Now third property. The third property obviously is if you are having a very huge charge body, then the surface will be carrying the charge but not inside. Inside the charge will be completely zero. Okay, outside it will be highest. So if you draw the graph of charge, So basically it is 0, then it reaches, then it comes down. Okay. So gradually it decreases as you go away from the charge, spherical charge. Done? Any doubts?
No.
Sure?
Yes, ma'am.
Very good. Now let's do a study about electric field strength. Okay, let me give you the homework also. So today you will do the study of Millikan's experiment, just to understand how the charges behave. Okay, Millikan's oil drop experiment. Done. Now after this I am having electric field strength. Now let me tell you what is electric field strength. So electric field strength is basically, if this is my field and here I am keeping a charge, how much force, how much potential does it experience, that it will be getting attracted and getting repelled by the force. Okay, so obviously electric field is here. What the hell is happening here? Okay, here. So here I am having the electric field, obviously. Okay, so the direction will be plus to minus. So this is a positive charge. It will be attracted towards this side. Done. So how much does it experience? So it will be experiencing F over Q. Okay. So this much will be the electric field strength it will experience. Any doubts?
No, no.
Sure. Okay. So if we are having these type of field lines, it is uniform in nature. If we are having curved lines, it is non-uniform in nature. Okay.
Yes, ma'am.
So how examiner will going to ask you? They will give you the plates. Plus plate, minus plate. Plus, plus, plus. Minus, 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 minus. So you have to draw parallel lines between them to show uniform field.
Yes, ma'am.
And you have to draw curved lines to draw the non-uniform field. Understood?
Yes, ma'am.
Okay, it is my bad. The arrow should be upward. The charges shall I change? We shall change the charges. Yeah. These are minus. Here are the plus. Okay. Done. Now after this. Okay, any doubts till here?
No.
Okay.
This one will, the arrow for the other one will be from positive to negative, like this, curved, like a semicircle, ma'am.
Yeah, obviously. Non-uniform
And
will be shown like this. Yeah, it will be shown like this.
Okay.
Yeah. Any other doubt?
Yes. No, I have seen another diagrams with the different, like there will be the left, there will be like a semicircle, right, there will be a semicircle, centered, there will be some particles. Is there a diagram like that, ma'am?
Please show me tomorrow.
Like,
Please show me tomorrow what type of question and answer you are talking about.
okay.
Okay.
It was like this.
Draw it. Yeah, so
I
it is
don't
going like
remember
this
much,
is
but
repelling each other, no?
yes,
They are
ma'am.
repelling each other. If
Yes.
I have plus charge, it will be producing this type of field.
Okay, ma'am.
Understood? They never
Yes.
intersect each other, no?
Yes, ma'am. Yes,
So they will be approaching, yeah. So repelling each other. This is repulsion.
okay, ma'am.
Okay. Yeah.
Yes.
Any other doubt?
No, ma'am.
Okay. So now after this, we are having electric field. Okay. One more thing, Akshita, Coulomb's law. is very much similar to your universal gravitation law. Okay, that in both the laws it's a central force, that in both the laws we are applying the radius, the distance from the centers of the two masses and the two charges. Now both the laws are very much similar in the way that they are directly proportional to the product of masses, here also directly proportional to the magnitude of their charges. Done.
Yes, ma'am.
Similarly, it is also following the inverse square law. Check here. And that is also following the inverse square law. Correct? So these are the comparisons. But yeah, where they are different, this force is attractive as well as repulsive, whereas gravitational force is only and only attractive in nature. Okay?
Yes, ma'am.
Okay. Anything you want to ask?
No, ma'am.
Let's do the next topic, and that is electric field and energy. So basically, suppose I am imagining that I am having an uncharged sphere, okay, and I bring a and I'm charging it by taking one at a time, and some small positive charges from the greater distance I am putting over it. Okay, let's have a look how I am doing it. I'm having an empty sphere, okay, and I'm trying to charge it. How I'm bringing the charges towards it, and I'm actually putting it over the sphere.
Yes, ma'am.
Can we have a diagram? Yes, we can. Let's just have a look over this. Check. Okay, I'm making this sphere to be charged, and I'm bringing it one charge, and I'm putting it over here. Done? Understood?
Yes, ma'am.
So as the charge on the sphere gets bigger and bigger, it would be more and more difficult to add the charges. Why? Because the strength of the bigger charge will repel the smaller charge with a very high force, correct? So we need to do more work.
Yes, ma'am.
Okay, so as we are pushed the charge onto the sphere, we would do some work, okay, and to transfer the energy to the charge, correct?
Yes, ma'am.
Okay, so now what will happen? This is known as electrical potential energy, which is equal to the the amount of work done in putting each charge over the sphere.
Yes.
Understood the scenario? So the
Yes,
electrical
ma'am.
potential energy is defined as how much work you are doing in bringing each charge from infinity to a given point. Okay?
Yes, ma'am.
Okay. So I'm defining here the potential for you. It is given as V. Okay? So the amount of work done per unit charge in taking a small positive charge plus Q from infinity and putting it onto the sphere. Correct? Okay.
Yes, ma'am.
So that means my work done will be defined as work done over Q, where work done is nothing but F multiplied delta S over Q. So what is F? Obviously we have calculated it. Okay, now 1 upon 4 pi epsilon naught, Akshita, is K value. Okay, overall. And the value of K is also having a number. Let me take it out. Yeah. K value, this is given in your formula booklet, 8.99 into 10 raised to 9 Newton per meter square per coulomb square.
Yes, ma'am.
Okay. It's not per meter square, but it is nearly Newton meter square per coulomb square. Done? Okay. So now
Yes.
I'm writing the thing here. It is K Q1 Q2 over R square. Delta S will also be R, and here I'm dividing it with Q. So R and R will get cancelled out, and this Q is nothing but the Q2 value, obviously. Who is experiencing the charge force? Correct? Remember?
Yes, ma'am.
Okay. So here the two charges, this is plus Q, this is small q, which is coming in the area of this, the bigger charge sphere, and experiencing a force of repulsion. Okay.
Yes, ma'am.
So work done to bring per unit charge into the area, and force is Q1 is capital Q, Q2 is small q. Okay, the small q and small q will get cancelled out. I'll be remaining with K capital Q over R. Making sense?
Yes, ma'am.
So the SI unit will be joule per coulomb for voltage, not voltage, potential. Okay. And
Yes, ma'am.
as you go away from the sphere, that is this sphere, as the R is increasing, you will get this type of graph. You do not have to touch it exactly to the zero line, but it will be something like this. Okay.
Yes, ma'am.
Any doubts?
No, ma'am.
Sure.
Yes.
Okay. So now after this, I am having a topic. Oh, the time is up, Akshita. Let's continue it in the next class. Okay.
I'm just copying the graph, ma'am.
Suddenly.
It's
Oh, it's okay. It's okay. I'm giving you. I'm giving you. Don't worry. I'm giving you the graph. I have not seen the time. I'm really sorry.
it's okay, ma'am.
Yeah.
Yes, ma'am.
Is it done?
Yes, ma'am.
Okay. So bye, Akshita. Let's meet in the next class.
Yes, ma'am. Bye, ma'am. Thank you, ma'am.
Okay.